And this is our current and last exam 2 related topic, which is a Doppler effect, which is a change in the perception of the frequency of the sound experienced by an observer when the observer and the source move relative to each other. So the most important, the key equation is on the screen. We just need to remember, like every time in physics, when we write an equation, all variables supposed to be related to the same object, to the same reference frame. Otherwise, it would be wrong. And well, I've got, oops. I've got one simple demonstration. All we need is a source of the sound which can move relative to us. Well, you can't run in this room. Plus, the relative motion should be relatively happening relatively fast. So, unfortunately, this room is small, so I don't have much room. But let's see. That's all I can do in this environment. Well, except maybe one more thing. It has to move. That's all I need. So let's move. That's a target. I haven't done it a year, so, and I haven't been practicing, so it's 50-50 chance. Oh, I broke it. Well, I'll fix it. Not now, not today. Next time I'm going to use it probably in several months. So, thank you. It's just a speaker and a battery. That's it. Speaker, battery, and a cover, nothing else. And of course, I should have been practicing. Still works. But I also have a simulation. So you saw a demonstration, there's a simulation. And we will talk about different aspects of this phenomenon. So first we should start from a situation when everything is at rest to refresh how we relate different variables. Then we have to move on to a situation when the source of a sound is moving, and then when the observer is moving, and then we arrive at the equation which has a name, the Doppler Effect equation, and then we will practice in using that equation. And these are just examples of the straightforward application of this rule. So if we write an equation like that, like this, all variables supposed to be related to the same origin, to the same reference frame. And in this situation, in general, we can choose 3 different reference frames. One is related to the ground. Second might be related to, well, a car or something else, doesn't really matter. The third might be related to a person, and whichever is a source, whichever is an observer, depends on actual situation. So if this person runs and screams, that's the source of a sound, the waves traveling away. And if we have a fireman in this car listening to that scream, that will be the observer. So every time we have to be very specific what object represents the source of waves, what object represents the observer, and then we can write this equation for all possible observers in the universe. So when everything is at rest, of course, everything is very simple. And the only kind of specific part is that we usually, well, we used to talk about velocities, but the equation which we will derive doesn't use velocities, it uses speeds, and the difference between velocity and speed is, velocity is a vector, so it points left, right, yeah. But a speed is always a number, positive number, or zero. So, and here, in general, we may have, well, the most common reference frame, ground, and there's always an observer, an actual or imaginary, smiling. And again, could have been a source of a sound, and an observer, and nothing is moving. So this is a standard representation of a speed of the sound source relative to the ground. So we should remember that when we say speed or velocity, it doesn't mean anything. The full name is speed of the object number 1 relative to the object number 2. And we assume that everything is measured relative to the ground. Now we cannot make that assumption anymore. In general, we have to pronounce the whole thing, yeah, the speed of the sound source relative to the ground. Yeah. But in this situation, it is 0. And this will be the speed of the observer relative to the ground, which people just usually write like this, observer. And this is the ground. And of course, the sound source generates the sound waves which travel away in all directions. Well, technically, we can assume that there's a spherical pulsing sound source, and spherical waves travel away in all directions. But of course, we only care about that wave fronts which actually reach the observer. Because some wave fronts travel away, they will never reach the ears of that person. So we don't care about those, or those which go up. Yeah. We only care about wave fronts, sound wave fronts, which eventually reach the observer. And sound travels, of course, with a known speed. Usually we just write a v, but we mean that it's speed of the sound relative to the ground. Now, unfortunately, this looks exactly like speed of the source relative to the ground. So when you write something like this, you need to remember what it actually means. And, well, the easiest model which helps us to understand what's happening is to imagine that the sound source makes pulses with a given frequency, yeah, like 10 pulses per second, 100 pulses per second, yeah, and those pulses generate wave fronts traveling away. So let's say this is a snapshot of a situation at certain time set to 0. And normally, the most convenient situation to look at is in one period. So what's going to happen in one period? Well, in one period, in exactly one period, the location of this object doesn't change. Well, that's wrong. He doesn't move. Everything what helps to remember. There is only one thing which actually is moving, which is sound. It never stops. So in exactly one period, let's say this wave will travel exactly one wavelength. So let's make it red. So this wave will not be here anymore. It will travel one wavelength. I don't know, let's say this. All wave fronts will travel exactly one wavelength. So that will be distance traveled in one period. We call it the wavelength. And this will be equal to that speed of the sound relative to the ground divided by the frequency, or speed times time. We just need to remember these variables, period, frequency, also are relative. And we don't usually use any special subscripts, but we could, like, and people use various things like 0, or R, mean rest when everything is resting. So a lot of things here related just to accurate use of subscripts and notations. So now we have established a set of variables we will be using. So any questions so far? Well, a moving source. So the buzzer flies, and while flying, it makes a sound of a given frequency, and that might affect or not the wavelength. So what do you think? So the picture which we can draw now would look like this. A moving source, and wave fronts travel away, and the speed of the source is not 0 anymore, while speed of the sound is never 0, and the direction is the same for both velocities. Not is always the case, because as we know, there is also a wave traveling in opposite direction, away from the source. So when a source is moving, we always have sound which travels in front of the source, ahead of the source, and we always have sound which travels behind or away from the source. And we may have an observer listening to that sound here, or we may have an observer listening there. There will be some difference. This question is about waves which eventually would reach the eyes on an observer who is also in front of the car. So let's check the WebAssign. Well, probably we will not call it WebAssign soon anymore. By some reason today the direction of the mouse changed. So we're having a distribution. So people think, choose their answer. But again, it's very helpful practice to draw a couple of pictures. One which represents what is happening now, and second, which represents what's going to happen in one period. So now we see this one wavefront which starts moving away, and this wavefront travels at the given speed, and source travels in the same direction. So if we wait exactly one period, now the wavefront travels exactly one wavelength. So in one period, the wave will be at a different location here. That's how far it travels, one wavelength. Which kind of a wavelength? Well, that wavelength, which could have been for a resting source. But the source is not at rest anymore. The source has moved. So the source also now is at a different location. So the next pulse is being generated at a different location. So right here, right now, the new wavefront, the next wavefront is generated. And we can repeat the same picture again and again and again and again and again. So wavefronts will travel away from the source, having different distance between those fronts. And according to a definition, they all particles in wavefronts move in phase. That's supposed to be the actual wavelength in front of the moving source. So we can see that it actually is supposed to be shorter, less. We say sound wave shrinks in front of the moving source. And behind, what should be happening? Well, of course, at the same instant, there was another wavefront traveling in opposite direction. And that wavefront, relative to ground, should travel the same distance, but backward here. So in exactly one period, that wavefront is supposed to be here. And of course, when the sound source makes the next pulse in one period, we have a new distance between the consecutive fronts. That new distance represents the new wavelength, which now is actually greater than the wavelength of a resting source. By how much? Well, the distance traveled by the source equals the speed of the source times time, which is that very period we waited. So in this situation, the new wavelength will be old minus or old plus this product. So this is how we usually write it, minus or plus, and that's supposed to be this. Because period and frequency are inversely proportional. We just need to remember this variable, they related to this resting situation. Lambda, not lambda prime, is the wavelength related to a source at rest. So for this particular question, the answer is shorter. And here I actually do have a couple of simulations like this one. Oops. Do you work? Okay, this doesn't. Okay, interesting. The mouse does work. So you can see a moving source making pulses, and in front of the source, the wave shrinks, behind expands, and now it hits the end of the universe. Everything's frozen. Or another one. Let's say, so this is a resting source. All wavefronts distance from each other by the same distance, wavelength, but now the source starts moving. Well, right here, it moves at a half of the speed of the sound. Shrinking, expanding. Interesting. What's going to happen if it starts moving exactly at the speed of the sound? There's no wave, there's no sound in front of it. They travel at the same speed. That actually leads to a very strong accumulation of energy and sonic boom. And well, now we can travel faster than speed of the sound. We can't yet travel faster than speed of the light in the vacuum, but we can travel faster than speed of the sound. So everybody who's behind listening to this sound wave, hears very, very loud sound. The pilot doesn't hear anything except, well, how the engine works. Well, done. Done. And okay, that's the answer. Shorter. So this is the summary. The difference between a source at rest and the source moving. And this is an example of a relationship between the frequencies when the source is moving, but an observer is at rest, stationary observer. So what do we do? Well, let's just do it. So this person experiences sound waves hitting the ears, membranes, and for this person, the frequency experienced by the observer, the wavelength and the speed of the sound from the reference frame related to the observer, related by the same equation here. Now, of course, because the observer is at rest, speed relative to the ground and speed relative to the observer is the same speed. So this is just that old V. This is the frequency of the sound experiencing by the observer. And this supposed to be that new wavelength, which we know is supposed to be equal to this. But this old wavelength if you remember, the stationary situation also is related to speed and frequency. So we can simplify this relationship algebraically. V divided by frequency minus or plus speed of the source divided by the same frequency, which is this. The same frequency is a common factor minus or plus speed of the source. And now we can solve it for the new frequency. The new frequency will be equal to the old frequency times speed of the sound relative to the ground divided by speed of the sound relative to the ground minus or plus speed of the source relative to the ground. By the way, it's going to be in the future again, but we can simplify this. Well, some people say simplify, some people say more complicated. We can divide numerator and denominator by V. So this is 1, minus or plus this ratio. So technically what we see, absolute values of speeds don't really matter. For the shift of the frequency, only ratio matters. That's how that applet works. Yeah. This ratio could have been equal to a half. So the source travels at the half of the speed of sound. But if the source starts traveling at the speed of the sound, in front of of the source we get 1 minus 1, 0, 1 over 0, infinity. So we can't use this for that particular situation anymore. That's why something really strange starts happening when we reach the speed of the sound. And well, these are the equations. And for the observer behind the source, we just have to replace a sign. And here, we need to just, either get the clear understanding, when do we choose a minus, when do we choose a plus, or we should just memorize it. The equation is the same. When do we choose the minus? When the wavelength shrinks and frequency goes up. The frequency experienced by the observer is actually higher than it would have been when nothing would have been moving. And in this situation, we are, mathematically, we are increasing the denominator of the fraction, so the frequency goes down, the wavelength goes up. Well, now we're going to talk about a moving observer. So an observer doesn't know and doesn't care about the source, because an observer may not even know what's happening to the source. All observer knows is that wavefronts reach his ears and hit the membranes. That's it. So all we need to look at is the motion, relative motion between wavefronts, between sound and an observer. Mechanics. We have two objects. They both might move. And one object, which represents wavefronts, travels okay, we don't have any specific direction, so we can pick them. We can choose the direction. So this car makes a sound. Beep. That sound travels. And we have always an imaginary and real observer resting on the ground. But also an observer which is moving. And those guys both measure the wavelength of the sound wave traveling through them. So this guy has a meter stick and measures, okay, very, very resourceful guy, measures the distance between adjacent wavefronts is 1 meter. And this guy also has a meter stick, but he's not at rest, he's moving. And at the same time, looking down, measuring distance between wavefronts traveling in space. And what number would that guy be getting? That's what the question is about. That's a question number 3. What did you say? See, you reacted, so it's you. Next time, sit still. All right. So what did you say?
I think it's more than 100.
Well, yeah, I should have asked someone from the first row. All right. Any volunteers? Okay. She was first. Please try to walk and measure the distance. So this is 1 meter. I'm at rest. So this is exactly 1 meter. So please take it and just walk. Well, probably it's convenient to walk here and measure the distance and see if it's going to be different. But you can't stop. You have to. But you can walk very, very slowly, so you have enough time to measure distance. And tell us your number.
1 meter.
Okay, thank you. So it doesn't matter. It only matters at very, 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 very high speeds. Relativistic mechanics starts working. But for us in mechanics, in Newtonian mechanics, it doesn't matter if we move or at rest. When we measure distance between 2 objects, it doesn't matter if they at rest or if they also move. Still, the distance will be the same. So the fact that the observer is moving doesn't really change the number he measures or she for the wavelength. So if we have 2 persons, yeah, resting and moving, and if they measure the wavelength, well, technically that's supposed to be the wavelength. In general, we don't know if the source has been moving or the source was at rest. We don't know that. But if they measure this wavelength, they should get exactly the same result. So this observer doesn't move, this observer moves, but they measure the same wavelength. But something's supposed to be different for those two observers. Well, so this wavefront travels relative to the ground. The speed of the sound is a fixed number. But if the observer starts moving, the speed of the sound relative to the observer now should be different from the speed of the sound relative to the ground. And that's, again, the blast from the past. So 1 meter. The same wavelength. And the question, which is supposed to help us to refresh that knowledge. We used to call a law relating different velocities the law of relative velocities, but now we have to switch our mind from velocities to speeds. And in this situation, we have 2 objects traveling toward each other. So this guy travels at VO relative to the ground. This guy travels at Okay, Vu relative to the ground. The question is, what will be the speed of one object relative to another? If we talk about speed, so it's going to be a positive number. So the speed of u relative to the car and the speed of car relative to u will be the same, the speed. And this is the most important question for now. So, of course, the picture should help us. There is also simulation from PY105, which we, I think, didn't actually see at that time. It just tells you, so different objects travel, and you can look at it from relative views. This is, so this was a picture seen by this pink dot that represented you. But relative to a car, the picture looks differently. If we change the point of view, the picture looks differently. Why? Well, relative to the car means the observer is a driver of that car, so he or she doesn't move relative to himself. Everything else starts moving relative to. So when we change the point of view, now relative to the truck is stationary, but the ground moves relative to the truck, you, cars. And we always can apply the law of relative velocities, but there's also just a common sense approach. You know? If you have two objects traveling toward each other, right, this is and u. Toward. So relative to the ground, you have two numbers which represent the motion, but relative to u, u will be not moving. So relative to u, your speed is 0. So the question is, relative to u, this new speed, which we normally call a prime, should be equal to what? And you just have to look what speed, well, we used to say distance over time. But so that what is happening relative to the ground, relative to you, that's what's happening. That's you. So this will be the distance. And the distance actually doesn't depend on how you look at it. If this guy travels, let's say, I don't know, d1 meters, and this guy travels d2 meters relative to the ground, here this guy will travel d1 plus d2 relative to the ground. Or relative to you, sorry, relative to you. Because in exactly the same time, the space between those objects is supposed to be the same. So distance over time speed, in that situation, you have to add the speeds together. Any questions about this? So if this is at rest, this is how fast distance between the object changes. But if they move together toward each other, that means distance decreases faster. That means the speed of one object relative to another should be higher compared to a situation when at least one object is at rest. Well, now we know what to do. What we have is why all people today look sad? That's not right. So let's make him look proud. and the wave fronts travel toward or pass. Well, see, this is something what people sometimes get confused about. Wave fronts travel away. All right. That kind of means away. But a normal person can't run as fast as sound. So normal person just can't ever reach that wavefront. So that wavefront just travels away without anything. Which wavefront travels away and matters? Well, anyway, this is what we need to concentrate on right now. This wavefront eventually hits the ears of the person. And we know that equation which we want to use is supposed to relate variables relative to this person. So again, there is a new frequency experienced by this person, wavelength, and speed. And if we write the relationship, it should look like this. Speed equals wavelength times new frequency. But now this new speed also either old speed of the sound plus the speed of the observer relative to the ground, or actually I should change this to this. I should change the curvature here. That's what makes sense. Those wavefronts travel in the same direction, and they catching up with the observer, hitting the observer, generating the sound. But now the observer trying to kind of escape runs away. So now the relative speed will be less. So this is the equation. In particular case, if the source is not moving relative to the ground, in that case, this wavelength is equal to the wavelength measured relative to the ground for the resting situation. And in that situation, we can do the same type of the algebra. And this is a specific case. Resting source, moving observer. The new frequency of the sound experienced by the observer is related to the old frequency. S means stationary. You see, again, it's very important to know the exact meaning, because S might mean sound, S might mean source, stationary. When you write this variable, you need to know what you mean. So when everything is stationary, this would have been the frequency of the sound experienced by the observer. But when the observer is moving and the source remains at rest, the frequency changes. It goes up or down. When does it go up? When wavefronts and the observer travel toward each other. Why does it go up? Because in that case, the moving observer kind of hits the wavefront more often. More often. Yeah. Higher frequency. But when an observer trying to run away from wavefronts, but they catching up anyway because they travel faster, so they hit the ears of the observer with a less number per second, lower frequency. And of course, so this is an illustration for a case when wavefronts and observer travel toward each other. And in general, all we have to do is just finish that calculation we have started. So in general, the source might move relative to the ground. An observer might move relative to the ground. Sound waves always move relative to the ground. So that's a V. So relative to the observer, speed of the sound relative to the observer is supposed to be equal to the wavelength of the sound waves measured by the observer times the frequency of the sound experienced by the observer. That's what all those primes mean. Well, observer, okay. And speed of the sound relative to the observer might be equal to speed of the sound relative to the ground plus or minus speed of the observer relative to the ground. And it should be equal to, well, if the source is moving, that might affect the wavelength. So it should be the wavelength of the sound wave relative to the ground for the stationary case minus or plus the speed of the source relative to the ground divided by the frequency of the sound for the stationary case times the frequency we are looking for, the frequency of the sound experiencing by the observer. So that's a plus. I want to draw a good plus. And we just do the same thing we have done before. Or if we divide the numerator and the denominator by speed, for practical applications, for solving problems, I would usually use this, unless we don't know the speed of the sound, unless we only know the ratio. If we know the ratio, we can use this. Mathematically, it's absolutely equivalent approach. And this is the Doppler Effect equation. That's it. Well, I've tried to also draw more accurate pictures. I'm not sure if it's actually more accurate, but I still have them. If you want it, it's yours. So all situations starting from resting situation, the moving source, the moving observer, the general case, and we're done with the theory. Okay. This is our equation. So every time when something is happening, we should write this equation and make two choices. Plus or minus here, or minus or plus there. That's it. If we made the choices correctly, the rest is just calculations. And again, what helps us to make a choice? Well, again, this part of the equation is related to the motion of the observer relative to the ground. When the observer doesn't move, that's just 0. When an observer and wave fronts travel towards each other, the frequency should go up, so we should choose a plus. When an observer tries to escape, runs away from the wave fronts, the frequency should go down, we should choose a minus. What's happening to the wavelength depends on, well, the motion of the source and where is the observer. If an observer is in front of the moving source, that means the wave fronts which reach an observer travel in the same direction, so source fronts, and that shrinks the wavelength, which should increase the frequency. And to increase the fraction, we should decrease the denominator, we should choose a minus. And when the source travels in one direction and wave fronts which reach an observer travel in opposite direction, that expands the wavelength, decreases the frequency. And to decrease a fraction, we should increase the denominator, and we should choose a plus. So there are certain mnemonic rules. For example, which speed should go where? Observer should go in the numerator. So we say the observer should go on the top of the fraction. They both have the same letter O. Observer, top. Source, basement. And well, all we have to do is just practice. These are rules, and the most important part of the practice is choosing plus and minus. So the general strategy always starts from a picture. You know, in physics, every problem starts from drawing a picture. So, and your picture always has to show the source, what's happening to it, the observer, what's happening to it, waves, how does it travel. And then looking at your picture, you make your choices, and done. So let's practice. These are several possible situations, not all of them, but several possible situations. And we just have to practice in choosing a plus or a minus. So these situations also depend on mutual orientation, so we just have to draw some kind of a picture, adding one more column. Picture. A picture is always implied, so even if we don't have it, we have to draw it. It's too much, not enough space, so I'm going to call them 1, 2, 3, 4, and I'm just going to draw a picture one, and I'm going to choose so we can choose a source to the left to the observer, we can choose an observer to the left of the source. We don't have time to go through all possible situations. So in all my previous examples, the source was placed to the left to the observer. So now let's do it differently. Let's place the source to the right to the observer, but they travel in the same direction. This is a specific situation. Now, what's missing? A tree, which represents the ground, and a happy person looking at everything around. And what else is missing? A very important element. Sound waves, at least one front, because we need to know how it moves relative to the ground and relative to the observer. So in this situation, well, that arrow represents the speed of the source relative to the ground. This is the speed of the sound relative to the ground. And the observer has a certain speed relative to the ground. The equation is always the same. So now, for the top sign, we have to look at the relative motion of the wave fronts and the observer. That's what we call closing. So the speed of waves relative to the observer should be higher compared to the stationary case. To make it higher, we should choose a plus here. And you know what, let's call it, okay, 1A, 1B. Just for the practice, at least once, we will see how would it change if we switch them. Now, the source travels to the right, the wave travels to the left. So this wave is behind the source. So wavelength should increase, which means the frequency should decrease. So we should choose a plus. Denominator, make it larger. Now that's 1A, 1B. Don't hit me. That's why he runs away. I will hit you. That's what he screams. So, observer and waves. Now they travel in the same direction, which changes the relative speed, decreases it. So again, imagine if the observer is at rest, waves travels like this. But now, an observer also moves slightly away, so it slows down the closing. So now, the frequency of the sound experienced by the observer should go down, and we should choose a minus. So this is, now let's do it, okay, 1A, 1A, 1B, 1B, and now the source kind of squeezes the wavefronts, the wavelength shrinks, frequency should go up. So for the denominator, we should decrease it, we should a minus. Plus, a plus. No, a minus. Just a sec. Let me think. Sometimes I really need to think. So what did I say? We decrease this, and no, it's a minus. And we should decrease the denominator to increase the frequency. That's what it is. The frequency should go up. You look confused. We don't look at the observer anymore. It doesn't matter anymore. That's what we're looking at. This moving source kind of compresses the wave in front of it. So wavelength should go down, but if wavelength should down, frequency should go up. So we should decrease the denominator of the fraction. To do that, we have to select a minus. You can use a logic like this, or you can just memorize all possible situations. Let's do one more. All right. Someone has to pick this, or that. First is done. So second, third, or fourth. Gentlemen in the back, what do you think? third one. So we're going to do the third one. And these velocities, these arrows represent velocities of a source and velocity of the observer. So the source travels to the left, the observer travels to the right, but the mutual orientation also is open. Again, a source could have been to the right to the observer, or a source could have been to the left to the observer. No, someone else. Please tell me, where do you want the source? To the left. Thank you. So that is a case 3, well, A, and that's all I'm going to do. You can practice at home. So that the source, that's an observer. An observer runs to the right, and the source travels to the left source observer. Now, of course, only those wave fronts which hit an observer matter. Wave fronts travel away from a source in all directions, but only these eventually reach the observer. Only those matter. So we should draw waves which travel to the right. And that's it. Bless you. So the numerator, is related to the relative motion between the fronts and observer. Now, here we have to make a choice, a plus or a minus. What do you think? Well, a plus or a minus? You can't dream during physics class. Minus. If they would have been closing, we would have to choose a plus to increase the frequency. So to do the opposite, we have to choose a minus. And the bottom sign is related to what's happening here. Now, the source and fronts travel away from each other. So how should that affect the wavelength and the frequency? What do you think? Yeah, so the wavelength behind the source is larger. If we compare it to a stationary situation, increase in wavelength means decrease in frequency. So we have to decrease the fraction. So to do that, we have to increase the denominator. And to do that, we have to choose a plus. The rest is just practice. So a question. If I had my buzzer working, I could do this, but I can't anymore today. So you have to use your power of imagination. You can imagine this is you on a swing. So you move back and forth listening to music. And that, well, if you move fast enough, you can actually hear the change in the pitch. So the question is, at which location you would experience the largest change? If you were at rest, you would hear something like this. woo. But when you move, you hear woo, woo. Where? Well, that actually technically just the application of our knowledge of simple harmonic motion. The highest and the lowest means it should be the location where it travels as fast as possible, the highest speed, but where the speed is highest for the ball on a string. Where? So it stops there, and on its way down, it always speeds up. So the lowest and the highest pitch will be heard when the boy travels through the equilibrium. That's it. So this, it's just a ball on a string. Speed is equal to 0 here, and speed reaches maximum at the bottom. But the direction is different. It moves toward a speaker or away. So that affects the tone highest and lowest. Well, I'm going to give you time to read this problem and set up a situation. Choose a plus or a minus for wherever you want to. High-speed train is traveling at a given speed and makes a sound, a horn. The frequency 415 is relative to the person moving in the train. So it means relative, if the train would have been at rest, that would have been the frequency of the sound experienced by a resting observer. And we have to imagine we are inside. But when a person on the ground is listening to the same sound, that person should experience some change in frequency. And one change happens when the train is approaching the resting observer. And the second happens when the train moves away from the same resting observer. So if the observer is at rest, this number equals what? Well, no one else can see it. No one else can see it, so you have to say it. 0. So this is done. And here we have to choose a plus or a minus, depending on a case. So, case A, approaching. I think I should have a slide. Was it coughing or sneezing? If sneezing, bless you. A, B. So we don't really know the actual direction, so we can choose. Let's say it moves to the right. So in case A, this is 0. That's the source moving. These are waves moving, and the new frequency should be equal to the old frequency times, well, 1 plus or minus 0 over 343. 1. Now that's supposed to be 44.7 divided by 343. The only and the only choice we need to make is what to choose, a plus or a minus. And in case B, we have the same resting observer, but now the source will be traveling away. So this is the wave front, which travels toward the observer now. So now the frequency should be equal to this number, again, 144.7 over 343. And again, we have to choose a sign, but of course, the opposite to case A. So for a case A, what should I write here? A minus or a plus? Minus. It's a situation when wave fronts are in front of the source, so wavelength shrinks, frequency goes up, the denominator should go down, we should subtract these numbers, and here we should add. And I believe I even have the numbers. So, any questions? Here we also have calculation of those wavelengths. One is in front of the source and second is behind the source. We can see the different. How do we calculate the wavelength? Well, it's speed over the frequency. We just have to remember that all three variables must be related to the same reference frame. This is the resting observer, which is ground. Resting observer means ground, so speed of the sound relative to the ground, frequency of the sound relative to the observer, which is different, wavelength. Any questions? This is a standard strategy, and I believe I just have several more examples. So tomorrow we will have like 15 minutes for Q&A. So please prepare cues. A stationary observer. Okay, stationary observer. So this problem is physically equivalent to this. An observer is at rest, the source is moving. So the strategy is the same. We only might need to flip what we know and what we're looking for. That's it. So if I know stationary observer, moving source, so same problem. We just have to fiddle with the variables. So a truck makes sound with a given wavelength in the air when approaching at 10 meters per second. Okay. So now we do it backwards. We know what a stationary observer observes, and we need, when the source is moving, and we need to say what that observer would have been hearing when the source stops moving. So, approaching. No motion here. Moving there. Fronts travel toward the observer. That's our equation. Well, I don't really write S or O. Because that actually confuses me. I write just prime and nothing. And the same equation, source speed. So Same situation, same sign in front of the moving source. It shrinks. We have to decrease the denominator to increase the frequency. And now we can start thinking a little bit. So what do we know? We know that the truck makes a sound with the wavelength of 1/2 of a meter when approaching. So that would have been the wrong symbol. This is this. This is the speed of the source relative to the ground. And the speed of the sound relative to the ground is 340 meters per second. However, since the observer is not moving, that's also the speed of the sound relative to the observer. And now, what can we do? Well, so we can calculate this frequency. The equation I want to write is for speed. That's my mnemonic rule. So when I write this equation, I start from either this or this. What is the difference? In this equation, all variables related to the observer, actual case, what's happening here, nothing has been moved. But we know that in this situation, these are the same. And we can use this equation, set it up, 340 will be equal to the frequency times wavelength. So the frequency will be equal to 340 over 1/2, 680. But we need to remember this. So I'm going to make a red arrow. Now this is this, what it is. But now we can just finally use this equation backwards. 680 should be equal to the frequency when the truck wouldn't be moving, 1 over 1 minus 10 over 340. That actually is not the way I like to write it. That's going to be 340 over 330. Let me just rewrite it immediately here in a more convenient equation for calculating things. That's going to be V minus 0 over V minus Vs. And now we can solve it for that new frequency, hence, and I don't have much space, so I have to do it in my head. 680 over 340, 2 times 330, 660. And finally, I can use this new number here to get the wavelength for a stationary situation. 0.52. So again, it proves that when nothing was moving, the wavelength was slightly longer, then it started moving in front of the moving source. It shrank from 0.52, from 52 centimeters to 50 centimeters. Any questions? Now an observer is running in a stationary track. So which number we can set to 0 immediately? Stationary track. Track is the source in this situation. So that's it. So we only have to deal with one part of the equation. Again, this is how I like to write it down, which is mathematically identical, right? This tells us that only ratios are important, but when we know actual speeds, why would we use fractions? See, it's 1, 2, 3, 3 fraction bars. So that's 0. What's left is here, and V is a common denominator. Well, so what do we know now? An observer running at 10 meters per second relative to the ground. The track doesn't move. And now this same observer, well, you see, people are resourceful. He runs, but at the same time measures the wavelength of the sound. Half of a meter. And the speed of the sound relative to the ground is 340 meters per second. All right, I might ask it tomorrow. So that is the speed of the sound relative to the ground. By the way, I want to ask you now, please tell me the speed of the sound relative to the observer. What should be the number? Just tell me a number. Thank you. This picture helps. The observer is traveling relative to the ground at, well, 10 meters per second, and the sound fronts travel relative to the ground at 340 meters per second. So the distance between these two objects closing faster than in a case when observer would be at rest. So the speed is 340 plus 10. 350 meters per second. Sound relative to the observer. Well, okay. Now, of course, we can start from, well, we can't use that equation yet because too many unknowns. We don't know yet neither frequencies. So what can we always do is to write the same equation which relates speed, wavelength, and frequency twice. Now some of these will be different, some of these will be the same. So what will be the same? We always start from the same. Something is the same. Anybody? Wavelength. When the source does not move, the wavelength cannot be affected. So this is the same number. So now what can we write? Well, what can we write? What can we write? We actually can do 350 should be equal to a half times this. 340 should be equal to a half times this. We don't really need that equation, but we could use it to check if numbers actually work. They will, of course. So this will be equal to 700. And that should be equal to 680. We didn't even, in this particular situation, we didn't even have to use. What did we use instead? This. So this or that. Because the first equation at the top was derived based on the second equation. But we don't have to do it every time. We can just use it to save time. Any questions? All right, finally, they both move. And I only have 4 minutes left. Don't answer this question. We just answered it a minute ago in a similar situation. So let's just do it. They close to each other. So, no, it actually runs away. So in this situation, if the speed, this is a very important word, if the speed of the sound relative to the ground is 340, but the observer runs away from wavefronts, so the relative speed decreases by 5. 340 minus 5, 335. So let's just do it. What can we write again? Same equations. And I don't know if I'm going to use all of them, but still I want to write all of them. Speed of the sound, speed of the observer, speed of the sound, speed of the source. I need a picture to choose my pluses and minuses. Again, don't hit me. Wave, front, traveling. So what we have is here source, observer, speed, and the numerator. We should decrease the frequency, a minus. The denominator. Oh, that watch is slow by 2 minutes. All right, I'm just going to add this. That should be another minus. In front of the source, wavefronts shrink, frequency goes up, and I'm going to start from this tomorrow. Thank you very much. But now you can just sit down and solve the rest of the problems. You're ready. You don't need anything else. So some of you are here who didn't pick up your exams yet, so please pick them up. And don't forget the change room change for the exam.
Can I get one of these? Can I get one?
Go ahead.
Thank you.
Good morning. Well, I got it on my card.
Oh, okay.
But actually, let's keep it. I might use some tomorrow.